Hello, my name is Bobby Schultz. I'm an electrical engineer. I'm a freshman at the University of Minnesota Twin Cities. Today I'm going to be talking about a project that I've been working on for a long time, and is any project in a constant state of flux and improvement. This is an LED lighting system that I developed because I was very curious about working with high wattage LEDs, and I had a very unique interface system that I wanted to have an interesting output for as well. So this is what I've done with that, and I'd like to show you that now. This video has been a project for Electrical Engineering 1301 class. This class has taught me a lot about a myriad of different things, mostly in the fact that I'd worked with many of these systems before, but this has given me insight into how they're used in a more professional level, what are other applications of these systems, and a more developed, more grown idea of how they can be used and how they can be implemented. This class has taught me much about how to work on a team, how to work in a group, and how to work towards a specific goal. Where in the past the goal was purely one set on myself, now the goal is one set by others around me. And so it's a different set of responsibilities. This class has taught me how to deal with that and how to rise to that challenge. So today we're going to be talking about the LED lighting system that I built. This here is the actual LED module itself. This contains the high-powered LEDs as well as the driver circuitry to them. It's completely modular. It has no cables completely connected to it. It's all has connector ports on it. The ports that go into this are a Cat5 Ethernet cable, which is where the signals are actually sent into this, which are what controls it from the main control unit, as well as the power, which is from a 9-volt, in this case 9-volt wall wart AC adapter, like this one here. Goes into the wall, your other end simply plugs in here, and that's what gives the power to this one. There is an identical wall wart adapter on the actual control unit. Alright, now let's open this up. Alright, so now I've got it open up. Let's take a look. So while we do have a lot of wires going around here, there are a few things that are immediately apparent. This large black section in the middle here is the heatsink. These are high power, high wattage LEDs, 3 watts a piece, meaning that you need a large amount of aluminum, in this case, to dissipate the heat that are generated by them. Otherwise you'll overheat them and short them out. Also on here you can see this is our Cat5 Ethernet port where the signals are actually going to be coming into it. On this side over here, this is our plug-and-play connector system. I wired up each of the LEDs so that it has simply a connector that is going to drop into this board here, meaning that none of them are hardwired into this system. Say, for instance, one of these LEDs were to overheat and get burnt out. From that, you could then simply remove that individual LED, drop in a new connector, and have it be replaced with no soldering or taking apart of this system required. I wanted a very modular system that I could adapt as my needs changed. Also here you can see that we have our driver circuitry. These are all N-type MOSFET drivers. They can handle a large amp load, which is obviously required with these high wattage LEDs. This here is a voltage regulator that is required that will give power off to all the LEDs in the system. On this side there's actually a chip set holder. This is for future modifications. In the future I hope to actually include a small Atmel processor on here, like this one for instance. This is an AT-Tiny85. It's a small microcontroller. I hope to include one of these in my projects because right now, as I'll talk about later, I'm sending an analog signal to this system over a length of Ethernet cable. In the future I'd like to send something like a digital signal, for instance a RC signal, or perhaps even a serial or I2C, ISP, signals of that nature. For that you need something to decode that on the other end, like a microcontroller like that. So I've allowed this to be in here. This is merely the lines coming in from your Cat5 port, which then go over to here. Right now they're merely jumped because, as I said before, I'm sending an analog signal. which is appropriate for an analog PWM signal, which is appropriate for controlling these driver circuitry that I have built. Also on here you'll see the power connector that I talked about before. And now perhaps let's take a more defined look at the circuitry. Alright, now to talk about some specifics of the circuitry. Here we have our 3-watt LEDs. The one in the middle is a 3-watt RGB LED. It actually has 3 diodes as part of it. This one here is a 3-watt warm LED, meaning that it has a Kelvin value of 4,000 right around, which means that it's going to generate a warmer color tone. To give you a benchmark, daylight is around 5,000, give or take. This, on the other hand, is a 3-watt cool LED, which has a Kelvin value of around 7,000, meaning it's going to produce very nice, pure, cool white light. To give you an example of what they actually look like when they're not mounted to the heatsink, here I actually have a 5-watt one that I've been playing around with, just to give you an example. They're just mounted to a flat aluminum disc. They're surface mounted to that, which then will allow you to mount to a heatsink, like so, and dissipate that heat from it. I've just mounted on these wires, again with the connectors, just for ease of use, but you can use them in any way, surface mounted or otherwise. Now, as for our driver circuitry over here, there's a few members of it. Firstly, there are several of these. There's actually 5 there because there are in fact 5 channels here. There's a warm channel, a cool channel, and a red, green, and blue channel. Each one of these is controlled by one of these. This is a P-channel MOSFET driver. This particular MOSFET driver is rated for 60 volts at 27 amps, so it can put out a great deal of power and deal with a great deal of power. That is why I've not had to heatsink any of these, because the power wattages that it's dealing with are minuscule compared to what they can deal with. A nice thing about these is that these are Z-type MOSFETs or Z-FETs, meaning that they can be controlled by logic level signals. So I can switch a 12 volt load with, say, from my microcontroller 5 volts. This is very helpful because you don't need external circuitry to what is known as voltage bump, so you have to bump up the voltage beyond it in normal MOSFETs. That makes these very easy to deal with and very helpful. Also over here on the circuitry, as you can see here with the heatsink on it, we have one of these. This is a 3.3 volt, 1.2 amp voltage regulator. Now, for those of you who are keeping track and doing the math on this, that does not come out to 9 watts of output. That comes out to something around 4 watts. However, that amperage load is merely a guideline and also means that that is going to be your average output without heavy heat sinking or without keeping that cool. I have not had any problems with this, pushing it beyond it. Also, given the fact that very, very rarely are all 3 of these LEDs going to be running at full power at any given time, which also helps with the wattage allotment. That voltage regulator does just fine dealing with the power constraints that are required. Now for a few of the things that are not necessarily circuitry related. This box that I have here is just a project box which can be had at any electronics store for a couple bucks. Here, as you can see, I actually removed the top with the Dremel tool, cut that out, and then introduced this plate here. This plate is actually not just a clear piece of plastic, it is what is known as diffusion material. This means that instead of simply being frosted, which is going to reduce your total amount of light that goes through it and simply soften it, meaning to break up any beam or something like that, this is actually known as diffusion material. What that means is that you can think of it as polarization. So it's going to actually bend the light going through it, meaning that instead of just softening the edges of the light that you're getting out of it, it's actually going to bend it outwards and spread the light out more, meaning that you get a greater area of it. The use that I wanted for this LED lighting system was to light my apartment. I wanted to be able to cover a great deal of the light on the walls in here with the light that I wanted from this, meaning that diffusing that light was very necessary. Also the fact that this, as anyone that has looked into, say for instance, an LED flashlight, looking into the diode itself is incredibly bright, especially with these high wattage LEDs. This allows that to be diffused, meaning that you're not blinded if you glance over looking at it. This also has allowed me to mount several nice things on it. I've mounted my Cat5 connector there, and up here I have a through hole with which I mounted my N-type connector here. Alright, so I already showed you the actual LED module that houses the LEDs and has the driver circuitry to them. Now this here is the module that's going to control all of it, or does control all of it. This is actually a lighting control board that I've retrofitted. It's just a bank of potentiometers, a couple rotary potentiometers and switches, but all I've really tapped into is the potentiometers, and I've added a button that I'm using as an interrupt, which I'll talk about later. Basically these are just slide 10K potentiometers. Right now I have these controlling the warm and cool LEDs, and these three controlling your RGB LEDs, and then this last one is actually a selector switch, which I'll talk about, where you'd move this to a particular position, hit that, and then that selects the mode which you desire. Here you can see we're using the same wall wart type connector that we used on the LED box, using the same power supply for it as well, just a 9-volt wall wart. On the back here, I don't know how well you can see it, but we'll be talking about it later as well. We have a same Cat5 connector cable, which is going to connect to the circuitry inside. Inside of this box, there's an Arduino Mega, as well as a breadboard and some minimal circuitry. So we'll talk about that in a minute once we break it open. Alright, so here you have the inner workings. It's a little messy just because I'm trying to add things on top of another layer that's already there, but that's something that can definitely be cleaned up and will be in the future. All of this here, all this green board and backing and hand soldering, that's all from the previous use of this. That's what all here are the potentiometers mounted to that you saw on the opposite side. Now here's all the things that I've added to it. Here you have the Arduino Mega, of course. What you have there is, and of course all these junctions and jumpers down here and up here. What all that's doing is tapping into the potentiometers that are on this board. These wires are here, they're connecting to the actual board that I've soldered into. I've energized all the potentiometers on the board and then pulled several of them off from there, from here, that you saw on the opposite side, the ones with the silver knobs on them. Those are going into analog reads of this board, and then also going into the board is over here. You're going to have, this is your selector button that I was talking about before. It's just a single pole, single throw switch, and that's connecting to the interrupt on the Mega, or one of the interrupts on the Mega. Here you have, this is your input jack for the power, which is mounted to the side panel, so it's obviously not on there right now. This here is the Cat5 connector I was talking about previously. I wasn't sure if you could see it real well, so I pulled it out of its mounting so you could see it better. I just have this on a solderless breadboard right now, just for convenience and for prototyping. I'm just running all of my lines from my board over to here and connecting into this very nice breakout board, which then connects into this system. This then is generally mounted into this back plate, which you can plug your Cat5 cable into, which runs to the box that I showed you previously, which actually has the LEDs and the drivers in them as well. That's the main advantage to this whole system. The way I wanted it was that that cable is the only thing connecting the two. There's no power running between them, and there's no other things that need to be connected. One cable for all of your communication, so that's definitely the upside. This board just mounted to the previous board that was already in here, and that's pretty much everything in here. This is definitely the more simplistic end of it, even though it looks a little more complicated. But most of this was done before I got into it. So next we're going to move on to talking about the code that's actually installed on this board, so you can see what all these inputs and outputs are doing and what I'm sending through here. Alright, so right now we're going to be talking about the code that I wrote for the LED control box that we've been talking about before. We can just start at the beginning here. So here, these are just several things that I've defined in terms of selector values. All that is going to do is add readability to my code. Here then next we have declaration of several analog input pins. These are the input pins that are connected to the potentiometers I referenced previously for the physical box setup. These are the potentiometers that are going to be controlling each one of these LEDs individually, depending on the particular mode. Lastly, there's the selector pin, which I introduced before, which is the potentiometer which is connected to the interrupt command. Then further down we just have declaration of different variables. These are all going to be constant type variables which are just going to affect, these are going to be user definable variables. These are things that I'm going to change depending on how I want it to perform, how quickly I want it to fade through certain systems, how long I want it to take per each step in other systems, and then what degree of fineness do I want? What amount of steps do I want per, for instance, color change? So we'll talk more about that later, but that's what these are defining up here. Then in our setup, we begin serial communication, which I'm using for debugging as well as communication to know what mode it's in, and then declare all of your outputs that will later be used as PWM writing as outputs. And lastly, we're going to attach the interrupt that I discussed previously for selecting the mode. That's going to be in a falling state because it's going to low in that case. Now the actual main loop of this function is very, very small because we've done it all in exterior functions. In this case, effectively the entire main loop structure is just one switch statement, which is switching the term select. From that, it's going to go to a different function that will control the lights in a different manner. You have simple functions like these. You have a spectrum one, which I'll be going through briefly, as well as a random color one, which I'll also be going through briefly. This here is your default mode, which is the one that it defaults to. That is pure one-to-one direct control, meaning that you're going to have complete control over all of the systems using just the potentiometers and that there is no computerized control over it. Up here, this is just manipulation of variables, and I will talk about that in a little bit as well. Now, as you can see, there are several different, just very simplistic for loop type codes in here, but one that I want to talk about is this because I feel that it's a good demonstration of some of the things that I've implemented here. Actually, first, we should talk about this. So, in here, the way that these loops are moving through is on the idea of having a mode selection. So in the original main loop, there's that switch statement that we just saw. From that value that's being switched is select. We have the select value, which is going to be returned from this loop. In this case, what it's going to do is when the interrupt is triggered, meaning you're going to move the potentiometer to a particular location that you want, corresponding to one of these different modes, you're then going to hit the interrupt button, and it's going to call this function. In this function, it's going to go through a set of if statements and determine at what point is the potentiometer located. That's all these values are, is attempting to determine which bracket of that it's located in. So they're pure numbers that I've selected as to determine the most selectable based on the numbers corresponding on the potentiometer for the different levels that you could select. Then, once those are selected, you're going to have select val be made equal to one of these different things. This is what I was talking about before with the readability. Up at the beginning of my code, you'll see that I've defined each one of these names as a particular numeric constant. That means that here I can go and select, for instance, spectrum color, and I just need to say spectrum color. I don't need to say, in this case, I believe it's 3, because that would make readability of this code much more difficult. Now, as I was talking about before, this is the longest loop that I have in here, and while it's perhaps not the most complex, I feel that it's good to go through. This is what I've defined as the spectrum loop. The basis of this loop is that it will go through and generate every color value that exists in your general spectrum by, in a for loop type statement, bringing up different values of color. For instance, here you'll see in the comments that this one is going from all the colors off to having red beyond. This one's going to have red and green beyond. This one's red, green, and blue beyond. And that the fading aspect of this, with the overlap, you'll end up with, as you can see, a great many sequences. But in doing that, you'll end up with generating a loop that goes through every color in the rainbow, theoretically. Now, I just want to talk about one of these in particular because, as I said, these are all copying of it, essentially, more or less, just with different colors being manipulated at different times. So what I have here is that I'm saying this is a for loop structure, and dim was declared up top. So I'm beginning with dim is equal to 0, while it's less than spectrum step value, which is the number of steps I have declared for this spectrum. Then I'm going to say that dim is equal to dim plus spectrum step. That was also declared as well. This has to do with how fine the step it is. You could perform this step in 255 steps or less, theoretically, if you were to step in more than 1 degree per time. However, in order to, especially when the movement is slower, when you're going to be going through all these steps at a slower rate, you're going to want added steps, because otherwise you get a very choppy look, and then this is a way to do it much more naturally, I found. So from this, I then go and I'm going to come back to this line in a moment. I'm going to have an analog right here. First I have these two written to 0 because they're not going to be done with anything for this for loop. So in this case I'm manipulating the red LED. So I'm going to have the red LED be a value of 255 times your dim times your percentage, which if you notice, is declared up top. I can go back to that later if necessary. All that is declaring is a maximum percentage that it's going on. So for instance, say I wanted all of these loops to go only up to 70% of their max brightness. I could do that. I adjust this percentage value in order to do that. And then the whole thing is divided by the spectrum step value. This is causing that to then go through the proper number of steps in it and still end up with the same motion of going between, in this case, 0, this whole section here is going to go between 0 and 1, and then is multiplied, of course, by 255. If I were to adjust the per value for percent, I would then have this say I put per at 0.8 instead of 1. It's a float type value. I would have this entire thing go from 0 to 0.8, which then I would only have 80% of my maximum range of motion in terms of light values. And now down here, this was something I added in a later iteration of this code after I built it the first time, which is the fact that for this lighting, the idea that the spectrum control is going through and it's changing the light values in order to create an ambiance of the different colors of light. However, I still want to be able to control the actual punch of the light in terms of having my warm and cool high power LEDs to say, turn on the lights effectively to make the room bright. So I've removed this section of it from computer control. This is just pass-through now. So what I'm just doing is having the same as I would do in my default mode, writing the values of those two different potentiometers, meaning that I can have this entire code running like this, and it's adjusting all of the RGB values, and those potentiometers will not be activated in this case. However, if I choose to adjust the warm or cool LED potentiometers, that will be seen immediately as it's being written in each step as well. And then, of course, at the bottom here I have a delay for each step. Now, this delay is not separate from all other things. This delay is based on the fact that up at the beginning of my code, I define several things. I define, firstly, and here we can go to that point very quickly, up here I define how many steps I want to take, meaning that, do I want to do this in stepping of 100 different steps or whatnot, and then how fine I want those steps to be. So what my total amount going through is, and how many steps I want to make in that. So effectively what I'm saying is the fact that I can go through this in infinitely small steps, but then that change is going to be imperceivable. You could also do it in a very large amount of steps going by 1. However, then the change would be choppy. So it's a combination of these two, meaning that you're going to set each one of these values, and that'll define the time as well then. Your time is then defined up here. So I've set spectrum delay to 5, and then I'm performing math on it over here. Just to walk you through it, because it gets kind of messy over there, the idea that I have going behind it is that I set this to 5. With that value, and knowing these values, I can define how long the individual delay for each loop needs to be in order to accommodate the number of steps and the number of degree per step that you have. And so that's where these values are coming from. So now back here to spectrum, that's where you get that fade delay, is that I'm not actually punching that number in. That number is being defined based on how long I want this whole thing to go. So how long do I want it to take from red being off to red being all the way on? And that's a much more friendly user interface to deal with in terms of changing that than having to bust out your calculator and figure out how long each one of these steps needs to be in terms of milliseconds. I actually don't know at the present time how long this delay is, but you could figure it out by applying the appropriate math as seen above. Now back to this, which I said I'd bring up later. What this is doing is allowing the interrupt statement to break it out at any point. So what this is saying is, if that select value, which is going to select which one of these large loops you're going through, if that select value is not what it's supposed to be, in this case it should be spectrum color ID, which I believe is the number 3, but that's defined up at the beginning. If it's not that value, break. And this will break you out of this for loop. However, it's a cascading sequence. So the way that that would, that eventuality would happen is the fact that, say I'm going through this loop, I'm going through these, and halfway through the loop, this loop in particular could take a minute to go through. Halfway through the loop, I change my select potentiometer and I hit the interrupt button. Now I want to break out into some other loop. Well, the way that that interrupt statement is written originally, I have to wait till I get all the way to the end of this code before it will check it again, the way that just the code is written in general. So I need to break out of this prematurely. The way that I've set this up to do that is I'm saying now, if your select value is not equal to spectrum color, so I've selected something else, break. And that will break you out of the individual for loop. However, that then continues down, and you have a cascading effect that breaks you out of every loop in the sequence and then breaks you out of the function almost immediately. So as fast as it can check those statements, it'll break you out of your function and go to whatever function then is appropriate, since it'll return you to the main void loop. So now I'll just go through this one just to show you the differences as you're increasing, but it's effectively the same. The only difference here now is the fact that now I want to have red on at some percentage and then start at that point. Start with red on at some percentage that I left off at in the previous loop, and now increase, in this case, green. So here I just have 255 times some percentage, which I've declared above. In this case, it's 1, because I want it to be the max value. But again, say that was 0.8. Red would now be 80% of what its max value was, which it would have been where it was left off at from the previous for loop. And that's being a constant value. Now green is being adjusted, again, the same way red was previously, going from 0 to your max value, whatever that may be. And the rest portion of the code in each one has remained the same. Now the rest of these loops are just repetitions of this in such a sequence that you get all of the possible permutations of color in the entire sequence. Now there are a couple other codes, a couple of loops on here, excuse me, that work in a very similar manner to that, so I'm not actually going to go through those. One that I'll go through very quickly is this. This is just the standard default one, full color, which simply takes your values from your potentiometers and converts them, maps them in this case, using these values from an analog value, which in the Arduino's case is a value between 0 and 1024, and maps that into a value between 0 and 255, and then simply writes that value to the particular LED. And you'll see a demonstration of this later. That's very simplistic, but it's the core and what is used most of the time. Alright, so one other section of code that I don't actually have time to talk about, unfortunately, but I think that it was worth at least mentioning. This is a code that I'll hopefully be able to post something about later because I spent a lot of time working on it, but due to time constraints of this video, I can't actually go into detail about it. But the idea behind it is that it's going to actually generate a random value of color for a particular loop. It's going to go through and generate a random value for each one, and then it will go and write that to it, meaning that it's going to do what the spectrum control did, but it will do it randomly instead of sequentially. That, I think, is a pretty good workup of the code. There are other ones, there are other loops in here, but I'm not going to talk about them because they're very similar in design to the Spectrum, just with different color controls. So I believe that this is a good overview of the code, and I hope that it has been helpful, and I hope to talk more about it. Alright, so we've pretty much gone over just about everything that there is about this. Just to sum everything up, I'd like to do a real quick demo here. So as you can see, we've got just the one Cat5 Ethernet cable going between them, individual power sources for both, as I described before. Now I can show you how everything works. Right now we're in your standard mode, which means that there's direct control through everything. You have control for each of your variable color LEDs. You have warm and cool as well. Now if, say, you wanted to go through some mode, like for instance our Spectrum mode, you move it to where you want it selected in this range, which corresponds to the slashes already on there, and then you're going to select this button, which is going to be your selector button. Now it goes into, in this case, this is going to run through Spectrum mode now. Now, say I want to go into some other mode from there. Alright, this is whatever they wanted to have, is the fact that you can break out in the middle of a loop like that and move on to something else that it's going to be doing. Or in this case, move back to our original loop. And it'll break out of that and move into whatever new one you want to be in. So this is what we have. I'd like to thank you for spending your time with this. I hope that this can be informational, and I hope to post more about this. Thank you.